So the Lorentz force details how a single charge is affected by a magnetic field. But a lot of times we have not a single charge moving through a field, but a current moving through a field. And so we need to connect that movement of one charge to the constant movement of a whole bunch of charges. That's what we're doing today. So the magnetic force on a charge, as we saw in the last video, is QVB sine theta. Okay. What we want to know now is what is the force when we have multiple charges? That is, when we have a current moving through a wire or something. Well, here you can see that is I, the current, times L, the length of the wire, times B times sine theta. And you might ask, well, what happened to the velocity here, right? Where's that V that was in this equation? It gets sort of sucked into the current, okay? Because that's determining how much charge is moving past a given point. And so the per unit time that's in the velocity gets brought into the current here. And so we have a nice equation to figure out what the force on a wire might be that's moving through a magnetic field. This guy is going to work the same, our right-hand rule. We're still going to use our thumb for velocity, but in this case, the velocity is the direction of the current. So our thumb goes in that way, our fingers go in the magnetic field, and our force on a current here is actually in the direction of our palm. So we don't have to worry about negative or positive here. This has to do with the fact that current actually moves in the opposite. The electron, when we say a current is moving this way, the electrons are actually moving that way. Why? It has to do with the origins of when people were discovering this stuff, and we just never got rid of that convention. So with this version of the Lorentz rule, we can always use the palm as our force. So this force is on charges in the wire. It can have a couple of interesting effects. One is called the Hall effect. And in the Hall effect, charges within the wire are pushed to a side. Or this might be in a blood flow, for instance, where you have blood which is can be polarized, pushing to one side of the wire or one side of the channel. And this polarizes the wire across its width, right? So if my flow is through here, my electrons are pushed this way. I'm going to have a polarized wire. And then I can figure out, I can take a voltage measurement from this side of my wire or my channel to that side, and I can estimate the velocity of those charges moving by. And so this is the example of a blood stream. If this were blood moving through and we pushed the negatively charged ions to this side of the bloodstream, we could figure out the voltage across it and figure out the velocity of the blood flow there. Also, the forces on the charges can be transmitted to the wire itself. So if you don't have space to move those electrons, then the electrons will actually just move the wire. And so in this image, we can figure out by the right-hand rule that the wire would be pushed upward. So, do this. I'm watching you. Put your fingers off to the right, pushing left to the right. Okay. The magnetic field is, the magnetic field, your fingers go left to right. You may have to do some gymnastics to do that, but then your thumb is with the current pushing out of the screen, and the force is then upward. And then finally, we want to remember that the current itself creates a magnetic field, right? It's a moving charge, and it creates a magnetic field. And we can measure the strength of that magnetic field using Ampere's law for a single wire. So for a wire, we have here current, which we've done before. If we loop this wire like this, You can figure out that the magnetic field created by this wire, it always goes in a circle around the wire, right? That was the right-hand grip rule. Um, Notice that the fingers here are always pushing up through the loop. That makes a nice strong magnetic field through the loop. And if we wrap a whole bunch of wires like this with the current going the same direction, then our magnetic field through that, which is called a solenoid, is going to be consistent all the way through. We get a nice, strong, uniform magnetic field, and we can measure the strength of that field by this equation right here. So this is Ampere's law for the magnetic field around a wire. This is for a field at the center of a single loop. And this is for the magnetic field created by a solenoid, where N is the number of wraps in the solenoid, and L is how long the solenoid is.